Welcome to Model 18, Supervised Machine Learning Regression. In this model, we will present the linear regression method. In order to understand the linear regression method, we introduce the case study about the electrical motor for remaining useful life prediction. Before starting to present the linear regression method, we'll present the glossary. That's the basic concept that we use in this training about artificial intelligence. So we have the concept about artificial intelligence that we already discussed, machine learning, unsupervised machine learning, supervised machine learning, supervised machine learning classification, and supervised machine learning regression. We already discussed and presented all methods concerning unsupervised machine learning, supervised machine learning classification. Now we are going to start the supervised machine learning regression. Consider the different methodologies that we have in artificial intelligence that can be applied to the content of maintenance. We still focus on machine learning. Later on, we'll discuss about deep learning. The machine learning concept is the same that we already presented before. So since we have a data set that can come from a sensor or a non-destructive test, this data set is split in training data and test data. Then, by selecting a model, we use the training data to calibrate the model and calculate the error. After that, we apply the 30% of the data set that is random selected to test the model and to verify the model. If the error is acceptable, we come out with a new data set and make prediction. And based on the error of the new data set, we validate the model. Then we can use this model for similar data sets concerning the similar context that we are using from the very beginning. In case of a regression, we have the same methodology. We split our data set in 70 and 30%. We train our regression model. In this model, we are going to speak about linear regression based on the data set training data. That is 70% of our data sets collected randomly. Then we predict the error of our model. We apply the test data and predict as well the error by using the test data in the model that we created. And that is the phase called verification. After that, we come out with a new data set and test our model again. Then we can validate our model. We have different types of supervised machine learning regression. The first one that we are discussing in this model is the linear regression and also the hidden and lasso regression. In the end, by defining and using a data set with independent variables such as temperature, degradation, progression, signature, and remaining useful life, we will be able to define and predict a model that can predict the future remaining useful lives based on the future temperature values. The linear regression method aims to define the best straight line or plane that has the minimum distance of the projected point to such hyperplane. So here we have a clear example of different points that are defined for one independent variable and one dependent variable. We need to find the line that's fit bare to this point. Therefore, we're looking for a line that has the minimum distance that consider the projected point in this line. If we have three variables, we will have a plane. That's the concept is the same. The projected point, the sum of the square of the projected point in the plane needs to be the minimum. So mathematically, we can define the linear equation by this equation that we have alpha 0 plus alpha 1 multiplied for x1. In order to minimize the distance between the predicted and real values, we consider the square of this equation as represented here. the loss function or the error as the difference, as the summatory of each different point concerning the predicted and the real point value squared and divided for 2. Again, for each point that we have, we calculate the difference between the projected point and the real point, and then we get our loss function or error function. The linear regression aims to find the best equation that minimizes the loss. So that is represented for a minimum of the loss that's calculated by this equation. In order to solve this equation, we need to use partial derivative, consider the parameter alpha 0 and alpha 1. By applying the partial derivative, we get in this equation for alpha 0, and when apply partial derivative concerning alpha 1, we've got in this equation for alpha 1. Therefore, if we have a set of data, we're starting to apply this calculation to define these two, alpha 0 and alpha 1, then we can define the equation. Another important parameter is the RUL, that shows the coefficients, that means the coefficients correlation. The coefficients correlation is a value between 0 and 1. Closer than 1, better is the correlation between the independent variable and dependent variable. In our case, the independent variable is the temperature and dependent variable is the remaining useful life. So as close as is the RUL is close to 1, better is the relation. That means these 2 points are positively correlated. So if you want increase, the other increase. And in our case, if you want increase the temperature, the one's supposed to increase. And then of course, we can have a negative value of lambda minus 1. And then do not mean that the correlation is bad, but means that we have a high correlation. However, the correlation is inverse. That means if you want independent variable increase, the dependent variable will decrease. That is our case. A variation of a linear regression is what we call Hyde and Lasso linear regression. The Hyde regression model is a special case of linear regression that has the object to adjust the regression line with overfit results by penalizing the regression equation with a penalty term. So if you look on the red line here, let's consider that the training data set have only these 2 points initially. That means the data set has a low bias and very low variance. However, with a new data points are included in this data set, this blue one here, we'll see that's the line equation that we define for the initial 2 points have a low bias but have high variance considering the blue points. Therefore, to adjust this red line to the new blue points, we use what we call a penalty term here, and then we change the inclination of the line, and then we have a line that's better fits in all data. The new green line will have a higher bias from the training data but have a low variance with the test data. That's the object behind the Hyde regression. That's the same of Lasso regression. So if you look on the equation of Hyde linear regression, we have the same term that we have in the linear regression. In here we have lambda slope squared. The lambda is higher than 0, so you can put, for example, 1 and 2, and the slope is the slope of the equation. So if we're doing that summatory here in this equation, we'll find the minimum distance between the points by adding lambda and slope, that's penalty terms. And that is the objective of Hyde or Lasso regression. That is to minimize the distance between the point by including a penalty function term here. So the difference that we have in a lasso regression is just that rather than to have a slope squared, we have this slope represented like this equation here, and the principle will be the same. So let's take a look on an example of a linear regression methods. Concern that we have different types of failure of some equipments. We want to, based on this time, we want to use a linear regression methods to calculate the reliability function. So by using the terms that we had before, such as alpha 1, and using all the summatory that we are having here, summatory of x, summatory of y, summatory of x multiplied for y is already defining here what we define in this template here, the summatory of this line here. Is that what we've got in this equation? Then in the end, we've got with the value of lambda 1. Similarly, we need to find the value of lambda 0. That is already defined previously, and we need to apply this equation. Then we define the value of lambda 0 equal to minus 0.35. Then, of course, if we have lambda 0 is equal to beta natural logarithm of eta, then we can define eta, that's 3.8, in to predict the reliability based on the let's say the viable two parameters equation. So we have alpha and beta, so we have beta and eta, there are these two parameters. So this beta is equal to the alpha 1, and this eta is what we've got here by using the value of alpha 0 and alpha 1. And then, of course, by different type values of time, we can predict the reliability of such equipment. Another important aspect, of course, if you look on this equation, is how is the coefficient correlation. So we can see that applying this formula, we get the value that almost equal to 1. That is a perfect correlation. And this positive means as long as the time increase, the reliability will decrease. So they have a direct correlation in here. So the linear regression methods and other methods, when we apply the verification process, we look for error prediction. We already saw that is the cost function, as we call, is based on error, but we need to demonstrate that we have different error functions. So the first one is the mean absolute error, and that is the average of the sum of absolute value of difference between predicted and real value, as represented here. We need to be careful to not compare the data with different scales. We have a mean square error. The mean square error is measured by the square difference between predicted and real values divided for the total number of values, and we have the root mean square error. That's the one that is more used, that we have a root here, and we measure also the error based on this root. So different type of error, and it's very important, this error measurement, to compare different methods. So we are looking now the linear regression methods, but later on we'll see different other methods, such as supervised vector machine, tree regression, decision tree regression, or Gaussian regression, or stepwise fitting regression, and even the neural network regression. Then, of course, we can compare the error of each model by comparing what's the data, the values that they are predict for, compare with to the real values, and then choose the method that have the lower error in this prediction. And that is a very important aspect that we are using in artificial intelligence when you want to predict remaining useful life. And thus, this approach, this calculation is, of course, inside the algorithm, but what we're doing here by this training is to demonstrate how to use that, how are the formulas, mathematical concept, and application, how we can do by ourselves to get these values. So we look on each individual method one by one. So in order to understand the linear regression, let's take a look on electric motor that is affected by the temperature. So we have a temperature degradation progression signature that we know that is based on, that's the degradation increasing, the degradation based on the percentage. And then we have our remaining useful life in days. We have 500 days, and here we have 100 days, almost 3 months. Then the idea now is, by using this data, we want to implement our regression functions that enable us to predict the, let's say, the future remain useful life. So here we have the first plot by using MATLAB software. They plot this information that shows the difference between the true values and the predicted values. And then you see the difference, that's the error between these values. And then, of course, by applying the concept that we already saw concerning linear regression, we can define a line that are able to predict our remaining useful life based on the temperature degradation progression signature that we will have in the future. And that's the objective of the regression. So in the end, we have a model here. That is the result, how the MATLAB shows the result of our prediction. So we have an equation that we are able to predict the remaining useful life, the dependent variable based on the value of independent variable, that is temperature degradation progression signature. And here are the values from alpha 0 and alpha 1 that we use in this equation. Here we have a standard error, t statistic, p-value values for each one of this variable. And here we have additional information about the number of observation and the error degree of freedom, and root square error, as I mentioned before, is calculated here, and the correlation coefficients that is represented for the R square that we have here. So let's understand just what means standard error of the coefficient, standard deviation. So we have t statistic. T statistic is the ratio between the estimated parameter divided by standard error. And the p-value is by using the hypothesis of a t statistic. So that we've got this p-value. And then we see how good are these values in here concerning such statistic values, as well as the correlation. Okay. So in the end, we will have our linear equation to predict our remaining useful life based on future temperature signature progression values. So, and then of course we've got this alpha 0 and alpha 1. That's a result of our prediction that we have here. As I mentioned before, we have alpha 0 and alpha 1, and then automatically we've got our equation. Then based on this equation, we can predict future values of remaining useful life. So it's basically what we're doing here. We have in the beginning values until the temperature achieves 6.48, and then of course when temperature change a little bit, which are the values that we have in the future. And then of course our model are able to predict that and give the next value of remaining useful life. So we are doing a very practical exercise, and to see how does it works in practice. And the very important point is to always look, when you have a new point, which are the coefficients correlation, which are the error, the root mean square error of considering the real value and the predicted value, in order to define which are the best model that fits in our data, and then have always the best prediction of remaining useful life. So now we move to the MATLAB, and we do exercise step by step by applying the codes. So the code is similar to what we had before. We need to input a database And in this database, we are called a matrix called A that will read this database. Then we need to, in the second command, to shift our data in 70% for data training, 30% for test data. Then we need to define the data training matrix and the data test matrix. Then we need to train the model. So here we have linear model to training and here we are training the whole data set. Then we have a prediction for this whole data set. Then what we put in here was a second training for only data training and a prediction for data training, this command. Then we run a training for the data set and we predict the values for data set. And then of course we can plot different models here, and in the end we can even come out with a final model when using the applicative, the app. Okay, so let's take a look on how does it works in practice. If you want in the future use MATLAB, you know how does it works. It's just follow this command that you can get some prediction from the MATLAB. So now that we have our MATLAB open, the first step is to import our file. Now we are in the regression methods, and the first one that we are looking at are the motor. Then we look at this file, we import this motor 6, is the one that we demonstrate in example, and you can see that this one have the temperature degradation progression values, 15 values, concern, and the remain useful life. So we import this matrix, we close this template, then we have here in our workspace this data set, Excel file. So we'll read this file and we call matrix A. So the matrix A will come out with the whole data set that we had. So here we are, and now we go to the next command, that is to split this data set in training data and test data. So we split now the data in training data, 70% and this 30% here for the test data. Now the next command is I need to define the data training, the test training. So I'm defining here the data train. Now I will define the test train data set. Here we are. I just made a mistake, a small mistake here. Need to put a variable here. That will work fine. So here we are. We have the data test with 3 values and the data train with 10 values. So we can see that the data train is selected random, is a random selection of the test train. So we can see that the second value is not equal what we have here in the second line of the data set. And similar with the data test sample. So we have not these last 3 values, we have other values that was random selected from the data sets. So now I need to start to put my training command. That's the next command that I will include. So I will include here the MNGL. So we can see a linear regression model here that I'm using. So I have the MNGL for the linear regression. So that's considering the whole data set. So I have different information here. For example, I have the mean square error, the root square error are important information that I have. I have the formal linear regression and other information that I can look in details, but it's not necessary to dig inside this model file. Now I will predict the values concerning the whole data set. I know that the idea that I want to do is to use data training and test training. We'll do that, but let's just look on the whole data set just to see how the data fits and what we can get when we plot this data. Okay, so here we are. We have the prediction of our data. So here we've got the Ipson prediction is basically the remain useful life prediction for 14 values based on what the data as training by using the total data set. So now let's use training a model for data training and then for test training. So we are training the linear regression by using the data train. So is what we've got here. So that is the data train set. We have MDL ones, yeah. So here we can see the error, mean square error, root mean square error, and other information. Now I predict the remaining useful life by how the model learning by using the data train. That's 7% of the data set, and let's see how we've got as a remaining useful life. So what we're going to use a prediction model for data training. So you'll predict the remaining useful life from a data training. So I can see here the prediction of the data train that I've got. So if I click here, I have this matrix that is a little bit different that I've got when I predict the whole life cycle, but not too much different. You can see the values here is quite similar. It's not too much different than what we've got. And now I will doing the same for test data sets. The other 70% or you create the MDL command for a test data set. So I will include the command for my training, my test data set. So is what I have here. So you can see that they calculate the training the data set, and then now what I'm going to do is to predict the remaining useful life for data test. So that's the next prediction, and then for my test data, that's a small sample, I have these 3 remaining useful life. That's what I've got. So now what I'm going to do is to plot the different data sets to see how does it looks like the different prediction and equation of regression that I use concerning the whole data set, the training data set, and the test data set. So I plot the first graph, consider the whole data sets. So that is the equation that we've got. We can see that remaining useful life is decreasing when the temperature degradation progression is increasing. And then, of course, with this equation here, I will be able to plot my remaining useful life. So I can also consider the training data set. So I need just I need to include the same command here and just change the name of the plot for a plot 2. So I use this basically the same command, but I just need to put MDL1, and this MDL1 now is considered this data training, the training data set. So let's plot and see the training data set, so we can see that they have basically the same characteristics but with a small number of data. And then I can use, we can see with the test data sets. How is the plot with test data set? Let's MDL2 relate to MDL2. Here we are, is the data test. So, and that is the less precise information because I have only 3 points. But even though I have the same direction, but that's not so reliable because of only 3 points. So let's do the exercise to use the APP so to make this regression. So let's move to the APP. We need to choose now the regression learning here. So the similar process that we have in classification methods, but we are using the regression methods, the regression learner here. So it's the same methodology. We open our template, we import the data that we have from our workspace, we split our data sets in training and test data sets, and then we select the regression method to be implemented here. And then and that's how similar step that we had as I mentioned before. I just need to select my model. So we have the file motor 6. You can see that I can select the training data sets and the others. So they already select my function that I want to predict, and the predictor is the temperature. So I come out here, just split my data in just adjust for 30%. 30% this data is random selected to define my test data sets, and the other 70% are the training data sets. Then now the data will be organized in a template here, and will shows up how are the data in the template. So here we are. We have the remaining useful life. I just want to select the temperature degradation. So here we are. So we can have that's the remaining useful life degrades when the temperature degradation progression signature is increasing percentage here. Okay. So now the data is organized, and what I'm going to do is select one model. So I use the linear regression, and then I will run my simulation, and then the software will come out with the error of this linear regression. And then of course I will look on some results that I've got from this regression, such as the error, the graph that shows the predicted value and the error value, and other solutions. So it's very good when you use the app is very fast. You can see that just including the command for you also have some introduction, that's how to use the command by using MATLAB. But of course, whenever we can use the app, is very fast and easier to implement such analysis. And then in the end, we will have our results, and we import the regression model to predict new data sets. So that is the end, the validation process that we always do. We come out with a new data set to make the prediction, and then we try to look on what is the error tells us to accept or not the model. Okay, so you can see here that the result is coming. We have this is still training, but it's finishing soon, and then they will shows the error. So you can see here the root mean square error, so it's 54. So when you look at this 54, we don't know if it's good or bad. We need to compare with others to really check it out and see if this error is good or bad. So we have some graphic as well. The graphs that we have here is different that we had in a classification model. You need to pay attention to it, and by the verification process of the regression method is based on error. So the model will always compare the real value with the predicted value and measure the error. So we can see here the root mean square error. We can also have different other values here. So we can see mean absolute error and mean square error. We can see R square, that is the correlation coefficient correlation that we've got from this model. And here we can see, for example, response and predicted data. If we want to measure, have the idea about the distance between the error, we have some error measurement from this point, but most of the point have no error. Okay, and another interesting plot that we have is the difference between true response and predicted response. So show some points out of this line in here. Okay, we can see other graphs such as residual plots that shows the variation that we have when we predict our dependent variable that remain useful life. But the most important one is this one here, and the one that we plot in the workspace. So now what I want to do is to export my model. So I already performed my calculation. I want to export my model, and based on this model I will make some prediction. That's the valid, what we call the validation phase. So I am already, let's say, happy with the value, that I've got here from this analysis, from this error, and let's say, and then now I want to predict a new value of I use a new data set. So it's the same process that we have in classification. When I export the function, I have this function here. So all I need to do is to import a new function. So let's import now the functions, the new data sets, and then we validate this model by look on the error. So let's go to regression, and then we have these new data sets, the motor 7. So we can see that we have no definition of remaining useful life, and that's what we want to do based on the previous previous data set that we had. So we are considering now that we have similar motor that have the same application. Then we now have a model to predict the remaining useful life. What we need to do now that we import this model is just to type the name of the file here, the motor 7, then that will be automatically the prediction of remaining useful life. So here we are in terms of days, so the remaining useful life of the new file. And so that is the whole process. There are some steps that's very similar what we've got in classification, and that is our how we can make use of the final regression model, and then you in the end validate verify if this model have a acceptable error. If we have acceptable error, we are going to use this method and this model for new data set. And then of course that's the principle how you using, we are doing all the mathematics and the logic command algorithm that we're using to produce that. And of course in a asset management intelligence system, this data, as long as you input the data comes from a sensor, or you input from let's say a non-destructive test. So the system will do the calculation. But again, it's very important. That's the objective of this training. It's to demonstrate how such methods are implemented, the characteristics of the method, the mathematics behind, and the algorithm. And then, of course, if you want to do your own analysis, you can use the MATLAB. That's very I would say simplest compared to the others language that you need to define language to code and produce such a mathematic regression. So you can use that in your database if you have one specific analysis to be done. Okay, so what I would like to show is just to demonstrate, I will demonstrate it once. If we have, let's consider all different types of regression methods. So now what I'm doing is to compare the root mean square error with other root square error from other methods. So we still have here linear regression, but there are other methods that will be demonstrated later on. So we see that stepwise methods, we have a linear regression of one method that is called robust linear. We have here the tree method, the decision tree method for regression. We'll see later on, but the idea here is just to demonstrate that some methods such decision tree have a higher root mean square error, and by comparing the linear regression with a stepwise regression method with decision tree, the linear regression is the best one. But when we compare linear regression with a support vector, we can see that support vector machine have a smaller root mean square error when compared to the linear regression one. And that means in the end that consider linear regression, decision tree, and support vector machine. The support vector machine is the best method to be used that will give you a best prediction of remaining useful life, because in the end this method enables to have a small difference between the real values and predicted value that is calculated based on root mean square error. And then of course we can see other methods, for example the Gaussian process here, that have a smaller root mean square error when compared to support vector machine. So the Gaussian process in the end is the best method to be applied to predict your remaining useful life. So let's go to a conclusion. The advantages of linear regression model is an easy data visualization, well applied for well organized data, and easy to understand the methodology and the final regression results. In the end, we have a linear equation, and it's very simple to understand which are the values and the parameters that's related to the independent variables that give the value of dependent variable. In our case, we have only one independent variable, that's the temperature degradation progression signature that enable us to predict the remaining useful life. The drawbacks of a linear regression are the linear regression method is sensible to outlier data. So if we have a data that is away from the most of the data, so that will influence in the root mean square, because as we mentioned, we need to plot a line that fits better in the data, and then of course higher is the distance between the point and the projected line, higher will be the root mean square error. The high number of independent variables may compromise the regression accuracy. In this example, we had only one independent variables, but let's say that we can put process engineers like to use to work with different dependent variables to see the influence of the process in the equipment or a product. So if we have a lot of these independent variables, 5, 6, 10, that of course will compromise the result, because in linear regression we are not able to eliminate the independent variable that's not influenced more in the result. We have some methods, regression method, that we can do that. We'll see later on. For example, the stepwise fitting regression method is the one that are able to eliminate the independent variables that has no influence in the prediction of the dependent variable. But that's not the case of regression methods, and that's one of the limitations that we have in regression methods. And not good to perform a prediction with data with seasonality. So that means data that's data set that have up and downs values will in the end have a line that go in the average, and that's not will be a good prediction. So this linear regression method, supervised machine learning regression, is a chapter 7 for my book, new book, Artificial Intelligence for Maintenance 4.0. You can find all this theory and the case study, and everything that I discuss in here is written in there. You see all information there. So thanks for your attention. If you have some question, please come out with your question, and let's move to the next model.